Hello, welcome to the second lecture of the course. In this lecture, we will start discussing two-state system in quantum mechanics, and these systems are extremely important because of its application in quantum information science and quantum technology. In fact, later on while discussing artificial atoms, we will model those atoms as two-level systems. So let us begin. Two-state systems or two-level atoms, which are also referred to as qubits, are backbone of quantum technology if one is interested in quantum information processing applications. By a two-state system, we mean a quantum system where we have just two energy levels which are the most relevant and their corresponding eigenstate. For example, we can have a two-level atom or two-level system having energy 0 and E with the corresponding eigenstate denoted by say ket z and ket e respectively. In the real world, we can consider a spin half particle or a spin half quantum system as a two-level atom or two-level system, and we know that for a spin half particle we have only two states. One is the up spin state and another one is the down spin state, and they can be represented by these gates. And even in the so-called double well potential, if we have a double well potential like this, and if the energy levels, the low-lying energy levels, low-lying two energy levels are well separated from the higher energy levels, we can ignore all these higher energy levels and we can focus only on the two low-lying ground states, and we can create this system as a two-level atom or two-level system. Now, an arbitrary two-state system can be represented by a state vector, say ket psi, which would be the superposition of the ground state and the excited state, and with their corresponding coefficients Cg and Ce. Cg mod square gives the probability of finding the system in the ground state, and Ce mod square gives the probability of finding the system in the excited state. And sometimes this two-state system can also be represented in this notation where we will write it as say C0 ket 0 plus C1 ket 1. In fact, this is the most used notation when one talks about qubit. The Hamiltonian of a two-state atom can be represented by a 2 by 2 matrix. So we have say energy E and energy 0. This diagonal element refers to the energies, and the off diagonal elements has to be complex, and they have to be complex conjugate to each other because this Hamiltonian has to be Hermitian, and this off diagonal elements refers to any coupling existing between the energy levels. We can always shift the energy levels. Say here we have 0E. We can always shift the energy level such that we can shift it to this is 0 here, and here we can write E by 2, and this one has to be minus E by 2, so that the difference between the energy levels remains the same, that is E here. And this can be done by adding a constant term to the Hamiltonian. So our Hamiltonian, now here we have E by 2 and minus E by 2, and here the off diagonal elements are alpha star and alpha, and then we just have to add a constant term E by 2 0 0 E by 2. This constant term is of no relevance as regards physics is concerned, and we can just keep this part of the Hamiltonian. Writing the Hamiltonian in this form has a huge advantage, as we will see now. Let me write a general Hamiltonian for a two-state system as follows. Say H is equal to epsilon z minus epsilon z, and here we had earlier alpha and alpha star. Okay, so let me consider alpha as epsilon x plus I epsilon y, and then alpha star here would be epsilon x minus I epsilon y, and this will ensure that this Hamiltonian is Hermitian. These we can express in terms of the so-called Pauli matrices. So you may know about these Pauli matrices. There are three Pauli matrices: sigma x, which is 0 1 1 0, sigma y, which is 0 minus I 0, and sigma z, that is 1 0 0 minus 1. So in terms of this Pauli matrices, it is very easy to see that this Hamiltonian here, I can write it in a compact notation like this. I can write it as epsilon x sigma x plus epsilon y sigma y plus epsilon z sigma z, which I can further write in a very short form, and I can write it as h is equal to epsilon vector dot sigma, and epsilon vector has the components epsilon x, epsilon y, and epsilon this would be epsilon z, and this sigma vector, which is the Pauli vector, has components sigma x, sigma y, and sigma z. Okay, let me before I go further quickly remind you about some useful properties of the Pauli matrices. For example, you know that if you take sigma x square or again sigma y square, all of them would be equal to identity matrix. You can verify it very easily. So this would be identity, and the product of the matrices sigma x into sigma y, these are actually operators. So let me write it like this. So if you work it out, you will get it as I sigma z. Let me quickly show you. So sigma x is 0 1 1 0, sigma y is 0 minus I 0, and if you take the product here, you will get it as I 0 0 minus I, which you can write it as I 1 0 0 minus 1, and this is nothing but your sigma z. So this is I sigma z. Okay, similarly you can show that sigma y dot sigma x is equal to minus I sigma z. Okay, so this clearly shows that sigma x and sigma y does not commute. So we have this commutation relation sigma x sigma y is equal to twice I sigma z. In fact, sigma x and sigma y actually anti-commute, so you will have sigma x sigma y. So anti-commutation means you have to add it up, sigma x sigma y plus sigma y sigma x. If you add it up, you will get 0. In the similar way, you can show these relations sigma y sigma z is equal to twice I sigma x. So you note the cyclicity here, y z, then you have here x. Similarly, you can write sigma z sigma x. This commutation relation would be twice I sigma y. Let me now discuss about the dynamics of a two-level system when it is not driven by any external drive. The system is described by this Hamiltonian h is equal to epsilon dot sigma, this Pauli vector. To know the dynamics of the system, we have to find out how the Pauli vector sigma evolves in time. We can work out how Pauli vector evolves in time by using the so-called Heisenberg equation of motion. According to Heisenberg equation of motion, the time rate of change of an Hermitian operator A is given by this equation. dA dt is equal to 1 by I h cross, and the commutation between the operator A and the Hamiltonian. If the operator is explicitly dependent on time, then we have to take that also into account. So we have to add this term. However, for simplicity, let us assume that there is no explicit time dependence, and therefore we are going to ignore this particular term here. The Heisenberg equation is the result of the so-called Heisenberg representation, which is also known as the Heisenberg picture. It's called Heisenberg representation or picture. Let me actually digress a bit and briefly explain this Heisenberg representation to you. All you are taught about is the Schrödinger equation in your basic quantum mechanics course. You know that the time evolution of a quantum state is described by the Schrödinger equation, that is IH cross del psi of del t is equal to h psi of t. This is the Schrödinger equation, and from here we know that we can find out how this state vector evolves in time, and we already talked about it. This is the so-called evolution operator, and it tells us how the wave function evolves in time. In quantum mechanics, the expectation value of an operator with respect to a state vector, which gives us the average value of a physically observable quantity, is found by working out this relation. So expectation value of the operator A with respect to the state vector psi of t, which let us say it is normalized. Psi of t is normalized. That means that the scalar product is equal to 1 here. Here you see that the operator A is time independent, while the time dependency is in the state vector psi of t. Okay, we can write using the expression for the time evolution of the state vector, this relation. We can write down the expectation value of this operator slightly differently. What we can do, we can write it as minus I by h cross. We are just applying this here. We have it ht psi of 0 a, and here I have again e to the power minus I by h cross h of t psi of 0. If we now do it this way, if I take this part to the other side, then I will have here e to the power I by h cross h of t a e to the power minus I by h cross h t psi of 0. And now if I say that this is my new operator, if I define a new operator AH, which is, as you can see, the time dependency is now put into the operator while the wave function remains is now becoming time independent, then the expectation value of the operator A can be worked out by using this relation. And in fact, nothing is getting changed, only the interpretation is changing, whether you work it in the Heisenberg picture or in the Schrödinger picture. This way of representation where the wave function is dependent on time and the operator is time independent is known as the Schrödinger picture, and it actually depends which particular situation you are facing or the problem at your disposal. Depending on that, you can either use the Schrödinger picture or the Heisenberg picture. Now let me use this Heisenberg operator or the time dependent operator, and let me show you how to derive the Heisenberg equation. So let me first write the operator. So this is my Schrödinger operator now, and which is time independent. AS is time independent, and we have this time dependency is included here. Okay, now if I take the time derivative on both sides, it's very simple and straightforward, but let me show you how to do it. So if I take the time derivative on both sides, so I will have it I by h cross h e to the power I by h cross ht a. So here I will have e to the power minus I h cross ht, and then I will have another term e to the power I by h cross ht. As this is time independent, so now derivative if I take here, I will have minus I by h cross h e to the power minus I by h cross ht. Okay, this I can write as I by h cross e to the power I by h cross ht. This I can now write ha, okay, e to the power minus I by h cross ht, and I have e to the power I by h cross ht. This is as. Okay, I have here h e to the power minus I by h cross ht. So what you see, that this product of these two operator is now in the Heisenberg representation because of this factor here. As you can see in the Heisenberg representation, the operator is written in this form. So similarly is the case here. So therefore I can write it as I by h cross here h of a minus a of h, and let me put h here just to emphasize that here I am writing about writing these things in the Heisenberg representation, and I have this equation dA h dt is equal to this one. In general, we don't write the suffix h, so we can simply write it as dA of t dt is equal to 1 by I h cross a h, commutation between a and h. So this is the Heisenberg equation. Let us now apply this equation to the Pauli matrices. For example, let me first do it for the x component of the Pauli matrix, say for sigma x. Then the this Heisenberg equation says we will have d sigma x of dt is equal to 1 by I h cross sigma x and the Hamiltonian. Now here this Hamiltonian we know for the two-level system it is equal to, let me write here, this is epsilon dot sigma, let me write, open it up, epsilon x sigma x plus epsilon y sigma y plus epsilon z sigma z. Okay, let us work it out. So we'll have 1 by I h cross, or let me take it this side, I h cross to the other side, then I have this one, and I will have relations sigma x epsilon x, okay, epsilon y sigma x sigma y plus epsilon z sigma x sigma z. Now this is obviously 0, so we will have epsilon y. The commutation between sigma x and sigma y already we know, that was 2i of sigma z, and sigma x sigma z we have minus 2i epsilon z sigma y. Okay, or I can write d sigma x of dt is equal to, I have 2 by h cross, okay, let me write here, epsilon y sigma z minus epsilon z sigma y. This I can write little bit cleverly as 2 by h cross. It is basically the cross product of the vector epsilon and sigma, the x component. If you now you recall that a cross b, if I take the x component of it, then I have here ay bz minus az by. So similarly you can see that this is nothing but the x component of this cross product epsilon cross sigma. Okay, similarly we can get d sigma y dt is equal to 2 by h cross epsilon cross sigma, the y component, and d sigma z of dt is equal to 2 by h cross epsilon cross sigma, the z component. So now we can combine all these results and we can immediately write a equation for the time evolution of the Pauli vector sigma, and that would be d sigma dt is equal to 2 by h cross the epsilon vector into the Pauli vector. Okay, so this gives us the time evolution of the Pauli matrix, and this equation should remind you about the gyroscope you may have studied in your classical mechanics course. In the case of gyroscope, you may have encountered this equation dl dt is equal to omega cross L, where L is the angular momentum directed along the axle and omega is the angular velocity of the axle about the vertical. Actually L precesses around omega with angular velocity modulus of omega. So as L precesses around this vector omega with angular frequency modulus of omega vector. In fact, in the similar line, we can interpret this d sigma dt is equal to 2e by 2 epsilon by h cross into this Pauli vector, that this Pauli vector precesses around this epsilon vector with angular frequency 2e by h cross. Actually, to be rigorously correct, as you can see, this is an operator, so we cannot plot an operator as such, but what we can do, we can take the expectation value of the operator and then we can plot it graphically. I can show you. Let us say our epsilon vector is directed along this direction and this Pauli vector is directed along this direction, and we have to take the expectation value of this Pauli vector, and then it precesses around this epsilon vector in this way. So this is x-axis, this is y-axis. The expectation value of the Pauli vector is also known as the Bloch vector because it completely characterizes a two-level system. In fact, let me once again repeat that if we have a 2 by 2 matrix, say A11, A12, A21, A22, this can always be expressed in terms of the three Pauli matrices and the identity matrix. This is why knowing the Pauli vector gives us the complete knowledge about a two-level system. The Bloch vector, generally defined in the context of quantum information science, is discussed in a supplementary lecture. Now let us work out the eigenvalues and eigenvector of our two-state system, which is h is equal to epsilon dot the sigma vector. Let us work out the eigenvalues of this Hamiltonian. Before that, let me consider a simple case where, say, epsilon vector has only z component only. In that case, this Hamiltonian h would be simply, it would become epsilon 0 0 minus epsilon. That means there is no coupling between the energy levels, and clearly the eigenvalues of the Hamiltonian are here E is equal to plus minus epsilon, and the eigenvector corresponding to this value epsilon would be, as you can see, it would be simply 1 0, and eigenvector corresponding to the eigenvalue minus epsilon is 0 1. In the general case, it can be shown that the eigenvalue would be given by E is equal to plus minus modulus of this epsilon vector. Let me show you the proof. We have this eigenvalue equation that h is equal to, say, this is the eigenstate and the eigenvalue is E, and we have this ket phi, and let me first write it as epsilon dot sigma. It's applied on the eigenvector phi, ket phi, and we have this E phi. Applying the operator h again on both sides, we will get it epsilon dot sigma square ket phi is equal to E square ket phi. Now if I open this up, then I will get, let me write the complete term. You will get epsilon square x square sigma x square plus epsilon y square sigma y square epsilon z square sigma z square. Then we'll have epsilon x epsilon y into sigma x sigma y plus sigma y sigma x. Then I have, say, epsilon y epsilon z sigma y sigma z plus sigma z sigma y. All these are operators, matrices, Pauli matrices, and I have finally epsilon z epsilon x sigma z sigma x plus sigma x sigma z. Now we then this is applied on ket phi, and we have E square ket phi. Already we know that this is anti-commutation relation between sigma z and sigma x. Similarly this and all these terms, they anti-commute, so this would be 0. On the other hand, sigma x square this sigma y square sigma z square identity, so we will be left out with epsilon x square plus epsilon y square plus epsilon z square applied on this ket phi. That would be equal to E square ket phi. So you can see that E is equal to plus minus square root of epsilon x square plus epsilon y square plus epsilon z square, which I can write as plus minus modulus of the epsilon vector. So that's how we can prove it. Now let us consider a two-level system with the Hamiltonian like this. Say we have now epsilon z minus epsilon z, and now we have non-zero off-diagonal elements epsilon x here. Let me consider epsilon y to be 0, and then eigenvalues are of this Hamiltonian would be plus minus square root of epsilon x square plus epsilon z square. Let us assume that the coupling field or the parameter epsilon x is fixed. Say epsilon x is fixed and the parameter epsilon z is controllable or variable. We can control it or we can vary it, or it's a variable parameter. Let me plot the eigenvalue E as a function of this controllable parameter epsilon z, and we'll get something interesting here. If I plot the eigenvalue E as a function of the controllable parameter epsilon z, keeping epsilon x fixed, so eigenvalue is epsilon z square plus epsilon x square. Now when this epsilon z is equal to 0, you see E is equal to simply plus minus Ex. So say this is plus Ex, this is minus Ex. Again, if epsilon x is 0, this particular point, then you will have E is equal to plus minus epsilon z. So for E is equal to plus epsilon z, I will get this positive slope. So this is for E is equal to, in the asymptotic limit, you will have plus epsilon z here, and on the other hand, when epsilon x is 0, then here we'll have E is equal to minus epsilon z, and this means that these two energy levels are crossing each other at this particular point. At this particular point, that's the reason it is called the degeneracy point. This is called the degeneracy point. But when epsilon x is non-zero, this is non-zero, then these two energy levels will no longer cross, and we will have a curve like this, and this will correspond to the plus square root of epsilon z square plus epsilon x square, and another curve will get like this, and these two energy levels are no longer crossing, and this particular area where this crossing is avoided is known as the avoided crossing. This is called avoided crossing. What about the eigenvectors? Let us work it out. The eigenvalue equation we have is h ket phi is equal to E ket phi. As we are in two-dimensional Hilbert space, we can write ket phi as a column vector with two elements u and v. Our goal would be to find the elements u and v. Now from the eigenvalue equation, I have this eigenvalue equation epsilon z minus epsilon z, epsilon x plus I epsilon y, epsilon x minus I epsilon y into uv is equal to E uv, and from here one can easily get epsilon z u plus epsilon x minus I epsilon y into v is equal to E u, and from this equation I can write as epsilon z minus E into u plus epsilon x minus I epsilon y v is equal to 0. So we can write u and v. We can, if I take u is equal to say epsilon x minus I epsilon y, this if I take, to satisfy this equation I must take v as E minus epsilon z, and it has to be normalized. So let us say n is the normalization parameter, and because of the fact that this ket state is normalized, which means that we have u star v star, this is the row matrix and complex conjugate, and then you have uv, this has to be satisfied, and from here you can immediately get that the normalization parameter would turn out to be square root of E minus epsilon z whole square plus epsilon x square plus epsilon y square. Okay, to illustrate, let us again consider the Hamiltonian h is equal to epsilon z minus epsilon z epsilon x, and epsilon x, let me consider it to be fixed. Say epsilon x is fixed as I considered earlier, and epsilon z is controllable, is a controllable parameter. Then we obtain the E versus epsilon z plot like this, as we discussed a short while ago, epsilon E versus epsilon z. So we had these plots here. So they don't, when epsilon x is non-zero, they don't cross. This, we get this avoided crossing. Now let us find the eigenvectors at asymptotic limits. That means, say, at the points A, at the point B here, at the point C, and at the point D. Okay, so to do that, let me first show you how to get it at the point A. So at point A, at the asymptotic limit, actually at A, in the asymptotic limit, when I say asymptotic limit, it means that here I have epsilon z is much greater than epsilon x at the point A, and therefore I can take E to be nearly equal to epsilon z, right? You can see from the eigenvalue equation, eigenvalue E is equal to square root of epsilon z square plus epsilon x square. Now epsilon z is much larger than epsilon x, so I can consider in the asymptotic limit capital E to be equal to epsilon z, and from this eigenvector equation we have uv is equal to 1 by square root of, let me first write the normalization parameter here, E minus epsilon z square plus epsilon x square, and here I have epsilon x E minus epsilon z. Okay, now this is what we have, but now at point A I have uv capital E is equal to epsilon z, and therefore I will get 1 by epsilon x here, and here it would be epsilon x, and it would be 0, so therefore it would be simply 1 0. So this particular point simply refer to the eigenvector 1 0, and because this point C lies on the same line, this point C will also correspond to the eigenvector 1 0. In fact, you can do by rigorous calculation. These calculations are simple. You can show that the point C will also correspond to 1 0. On the other hand, this point B will correspond to 0 1, and by similar logic, point D will correspond to 0 1. Okay, what about this point P and this point Q when epsilon z is equal to 0? You can do the calculation and you can show that the point P correspond to the eigenvector 1 by root 2 1 1, while this point Q correspond to eigenvector 1 by root 2 1 minus 1. Let me stop here for today. In this lecture, we discussed a generic two-state system. We have written down the Hamiltonian and work out the energy eigenvalues and the eigenvectors. However, the system that we consider is not externally driven. This issue we are going to take up in the next class. So see you in the next class. Thank you.